Hi everyone, this is the first section of chapter 5, which is section 5.1, and it's called Operations with Polynomials. Throughout this chapter, we're going to look at simplifying different kinds of functions, excuse me, and in this section, we're dealing strictly with polynomials. So we're going to have, I think a lot of it's going to be a review of what you covered in your Algebra 1 class, so that means that we can move through it fairly quickly. Although we want to make sure that you have a firm foundation with it. So make sure that you definitely bring in questions that you might have when you come into class. But the first thing we're going to talk about is, I guess, remembering what a polynomial is. And remember, a polynomial is a many-termed expression that would have no negative exponents or variables underneath radicals. And when I say no negative exponents, that would be no negative exponents on variables. So we can talk a little bit further about that if you need more clarification again when I see you in class. But these are going to involve a lot of exponents. So the first thing we're going to look at is an exponent review. We're going to end up using the 4 basic operations that we know: addition, subtraction, multiplication, and division to simplify these. So you may want to get these rules back in your notes if you don't remember them from Algebra 1. And the first is the product of powers. So if I gave you something in the form x to the a times x to the b, we would simplify that as, boy, I can't write here, simplify that as x to the a plus b. So that means concretely, if this was x to the 5th times x to the 3rd, you would tell me your answer would be x to the 8th. Your quotient of powers rule says that if we're taking x to the a and we're dividing it by x to the b, where x is not equal to 0, if x were 0, that would make this an undefined scenario. But when we divide with like bases, we end up subtracting our exponents. So the rule says that we keep our base and we subtract our powers. So again, if this were x to the 5th being divided by x to the 3rd, that means we end up with x squared because 5 minus 3 is 2. Negative exponents. Now, negative exponents are things that we can't leave or have really in a polynomial function, but we may run into them in our examples for presentation purposes. And what we have to remember is x to the negative a is the same as 1 over x to the a. So that means if you saw x to the negative 3rd, that's the same as 1 over x to the 3rd. So there may be times where we have to rewrite in order to simplify. And at the same time, 1 over x to the negative a is the same as, as x to the a power. So 1 over x to the negative 3rd is the same as x to the 3rd. Keeping in mind, again, that x in these problems can't be equal to 0 because that would make our denominator undefined. So these are the first 3. Make sure that you get them in your notes if you don't remember them. Write down any questions that you might have. There are a few more on the next screen I'm going to go to. So I'm going to take the information off of here and move forward. 4 more. Power of a power. And that's going to be something that's going to look like this. If we have the quantity of x to the a to the b power. If you remember from previous classes, in order to simplify a power to a power, we keep our base and we multiply our powers together. So x to the a to the b becomes x to the a times b, or x to the ab. X to the 3rd to the 5th would be x to the 15th. And if you need more clarification with these, we can go through them a little bit more in depth in class, but since you've already seen them, I'm kind of doing just a brief overview of them. Power of a product would be a form that looks like this: xy to the a power. And when you have a product inside a set of parentheses and you're raising it to a power, you raise both factors to that power. So this becomes x to the a, y to the a. So concretely, if we had xy to the 5th power, that's the same as x to the 5th y to the fifth. A power of a quotient would fit this form, x over y to the a power. And similar to the product above, we take the numerator and raise it to the power and the denominator and raise it to the power. But keep in mind that y can't be equal to 0. So this becomes x to the a over y to the a. Along the same lines, if a were a negative exponent, so we had x over y to the negative a power, an equivalent statement would be this, y over x to the positive a power. And that would mean y to the a over x to the a. Excuse me, that might be a little bit new. So if you saw something like this, this is where x can't be 0, oops, and y can't be 0. So if I gave you x over y to the negative fourth, that's the same as y over x to the positive fourth, which would be equal to y to the fourth over x to the fourth. So all of these rules are going to be used somewhere, somehow in the problems that we're working with. The last is the 0 property, and you have to remember that anything to the 0 power, any base to the 0 power is always equal to 1, provided that x does not equal 0. And again, we can go through the proofs a little bit more if you really have questions about them, but this is something that you already have a background in. So that's why I kind of breeze through them here on the screen. Moving on. Let's see. We're going to talk about monomials here quickly. And a monomial, if you remember, we talked about it briefly this year, but you definitely have seen it from Algebra 1 class. A monomial is just a one-termed expression. So there's no addition or subtraction involved. There can be multiplication. And because we're going through this process of simplifying things, we know that a monomial is going to be simplified when these criteria are met. There are no powers of powers left. Basically, no parentheses with exponents outside. Each base appears exactly once. All fractions that might be in the problem are simplified. And last but not least, there are no negative exponents. So we kind of have to have that checklist in our minds as we go through and work with these problems, that each of these criteria are met so that we know that things are in simplified form. In these examples, we're going to use those properties and our knowledge of simplified monomials in order to go through and simplify these as much as we possibly can. So in the next set of examples, we're going to be asked to simplify each expression. We're going to assume that no variable is equal to 0 so that we don't get something to cancel out or make something undefined in a quotient. So looking at this, we have 3 monomial factors. This is 1, this is 2, and this is 3. They're factors because they're being multiplied together, and each factor is a monomial because it's just one term. So when we multiply monomial factors together, we multiply all of our coefficients, so the 2 times the 3, which is 6. Then we're going to look at our like bases. A to the negative second times a to the third. Since those are like bases and we're multiplying, we add our exponents together, which will give us a to the first, or just a. Then we're going to look at any other like bases we might have. Now, the b for the base is alone right there as b squared. And the c to the negative second is alone here as well. But when I write that, I realize that we have to make sure that we have no negative exponents. This piece, c to the negative second, is going to go into the denominator. So our final answer will be 6ab squared over c squared. That's a simple example of multiplying monomials together. The next one is going to be division with monomials. And we see that we have q squared r to the fourth divided by q to the seventh r to the third. So if we follow the rules exactly as written, the q's, which are like bases, and they're being divided, the powers would get subtracted. So we end up with q to the negative fifth. The r's are the other like bases. We subtract those powers because the bases are being divided, and we get r to the first. Now we know that we can't have negative exponents, so the exponent that's attached to the q, that entire piece will move to the denominator, and the r will stay in the numerator. There is another way that you can kind of look at this. When you look at the q's, we have 2 factors of q in the numerator and 7 factors of q in the denominator. Those 2 in the numerator will divide out with 2 in the denominator, and that leaves 5 powers of q in the denominator. And then you can kind of rationalize if there are 3 powers of r in the denominator and 4 powers of r in the numerator. 3 out of those 4 divide out, and 1 power is left in the numerator, which brings us to the exact same answer that we had, r over q to the fifth. So the moral of the story here is that there are going to be different ways to do these, and I'm not going to hold you to one specific route, but it does have to be mathematically sound, and that's what I'll be looking for as I check your work. So these were pretty basic. The ones that we will do together in class will be a bit more challenging because they'll be a little bit more involved. But just to get your minds jump-started again, this is the kind of problem that you're going to be working with. Now this part C says we'd like to take the quantity of negative 2a to the fourth over b squared and raise that all to the third power. So these are powers to a power with a quotient. The one piece that I always see students miss is they forget to raise the coefficient to the power. So each factor within that numerator has to get raised to the third power. So we are going to look at negative 2 to the third, and then a to the 12th, because we multiply a power times a power, over b to the 6th, because we're going to do the 2 times the 3. Now I want to simplify, excuse me, simplify one last piece. That negative 2 to the third can be rewritten as negative 8, a to the 12th over b to the 6th. Final answer. So a combination of things there where we, raised the powers to the power, then had to simplify the coefficient value that was being raised to the power. Again, like I said in class, I'm going to give you some that are a little bit more challenging so that you can combine some of the properties and kind of really incorporate the ideas there. One piece that we have to talk about as far as vocabulary goes is this idea of what the degree of a polynomial is. Now, I'm not sure if you've heard that word before, so it may be a new vocabulary word, and if it is, you should make sure that you define it in your notebook. But the degree of a polynomial is the degree of the monomial with the greatest degree. What the heck does that mean? So a polynomial we know is made up of many terms. That many-termed expression is comprised of individual monomials. So in order to figure out the degree of the polynomial, we have to look at the degrees of each of the little monomials, and the one that has the biggest degree is going to end up giving us the degree of the entire polynomial. So I'm going to illustrate that with an example on the next screen, and hopefully it will make a little bit more sense to you. So this example says determine whether each expression is a polynomial. If it is a polynomial, state the degree. So we have 2 things to look at here. We have to first of all determine whether we have a polynomial, and then if it is, we've got to determine what the degree is. So looking at part A, 1/4 x to the 4th y cubed minus 8x to the 5th. This, if it is a polynomial, would have 2 terms. We have to make sure that the exponents are positive. They all are. Exponents on the variables, so they all are. And we have to make sure that we have no variables underneath square roots, and we don't have that situation. So this is definitely polynomial. And in order to determine the degree of this polynomial, we look at the 2 individual monomials that we have here. The degree of the first monomial is the sum of the powers. That's how we determine the degree in general. So the degree here is 7. The degree here for the second monomial is just 5 because there's only one power of 5 on that monomial. So overall, we say that the degree of this polynomial is equal to 7 because that's the highest degree of all the monomials in the problem. So not a hard task. You just have to make sure you can identify the degree of each individual monomial that's in the the big piece of the polynomial. Excuse me, part B has the square root of x plus 4. Now looking at this to determine whether we have a polynomial or not, the big red flag for me is the variable underneath that square root. If you remember from your Algebra 1 class, a square root means a fractional power. So that's implying x to the 1/2. We can't have fractional powers, which means we can't have variables under the denominator. So this is not a polynomial, which means we can't determine the degree, and we would stop here. Part C, x to the negative third plus 2x to the negative second plus 6. We have 3 terms, but the first 2 terms contain variable bases, the x, that have negative powers. And that's not allowed in a polynomial function. So again, this is not a polynomial. If those powers were positive, we would say that the degree of this polynomial was 3 because x to the third is a higher degree than x to the second. So that's the basic idea of the degree of a polynomial. Not too tough, but you just have to make the decision on whether you have a polynomial first and then how to determine the degree of each individual monomial. I've got 4 examples here and then 1 real-world application, and then we'll be set to go. These next 4 examples are going to take into account addition, subtraction, and multiplication with polynomials. So simplifying, and you guys should be able to do this already. I shouldn't even have to go through this on the video, but I will just for your note-taking purposes. We want to subtract these 2 polynomials, 4x squared minus 5x plus 6 minus the quantity of 2x squared plus 3x minus 1. And we know that when we subtract, we have to go through and we have to change our signs. So that's one thing that you need to watch out for. And then just combine like terms. So we'll have 4x squared minus 2x squared, which is 2x squared. So those are the like terms there. Then we have negative 5x minus 3x because of the distribution of the negative sign, which is negative 8x. And then plus 6 plus 1 after we distribute, plus 7. No other like terms. Done. Pretty simple. Just make sure that you change your signs when you're subtracting. Addition is even more straightforward than that because all we have to do is look to combine like terms. 6x squared and a negative 4x squared is 2x squared. Negative 7x and positive 9x is 2x. And positive 8 and negative 5 is positive 3. So final answer. The next one, 3x times the quantity of 2x squared minus 4x plus 6. That's implying the distributive property across 3 terms. So this will give us 6x cubed minus 12x squared plus 18x. We don't go back to factored form. Simplifying wants us in this situation to just go through. If I wanted you to factor it, I would say we can pull out a 6x, and that would leave us with 2x squared minus 2x plus 3. And that would be the factored form of this. The last example here is to multiply a trinomial by a binomial. Now, when I look at this, I'm going to backwards multiply. I'm going to take the smaller termed polynomial and distribute it backwards into the bigger termed polynomial. So this gives me n cubed plus 4n squared minus 6n. Then I'm going to take the positive 2 and go through. 2n squared. I'm going to line up my like terms vertically. So 2n squared plus 8n minus 12. And then I'm just going to add. So I get n cubed plus 6n squared plus 2n minus 12. final answer through multiplication. So it's kind of an extended version of FOIL from what you've done in the past. And you've done things like this for me already this year. So I'm not really too worried about not touching on it too much. So these are kind of the rote examples. The last one that I have here is more of a real world scenario to see what you can do with creating a polynomial. So what we have in front of us says, the U.S. Department of Transportation limits the time a truck driver can work between periods of rest to 10 hours. So that periods of rest means 0 hours. For the first part of his shift, Tom drives at a speed of 60 miles per hour, and for the second part of his shift, he drives at a speed of 70 miles per hour. Write a polynomial to represent the distance driven. So our variable would represent the number of hours at either of the speeds driven. So I'm going to say x is going to represent the number of hours driven at 60 miles per hour. Now that means that if we're working between rest and 10 hours, then 10 minus x will be the number of hours driven at 70 miles per hour. So if we want to write a polynomial that represents the distance driven during this time, I'm going to call my function d of x. D for distance and x is the variable with respect to time that I'm going to use. So the amount, or the distance that was driven at 60 miles per hour would be 60 times x. Go for x number of hours at 60 miles per hour would tell us how many miles we went, plus 70 times 10 minus x. So we're going to simplify what we see in front of us to 60x plus 700 minus 70x, which will give us in the end negative 10x plus 700. So we just want to write a polynomial. This is a polynomial that would represent the situation that's described there. Not asked to factor or anything, so you can leave your answer like that. We like to write things in descending order, so that's why I switched everything around and put the x first and the plus 700 afterwards. So you might be given some problems when I see you in class that are going to ask you to take a scenario and translate it to your mathematical terms and write a polynomial that represents that situation. So this shouldn't be overly difficult for you, but again, I'm always open to questions and will definitely help if you do have those questions. So I will see you in class next time. Make sure you bring your notes with you so that we can go through questions and do the problem set that goes along with this. Thanks for listening.